Greetings, Global Digital Development Forum attendees. My name is James Chaika. I work for RTI International in the Research Triangle Park in North Carolina, USA. And it's my pleasure to speak to you today. My presentation is entitled Humans Need Not Apply, and I'm putting forward the possibility of greatly reducing the role humans play in generating training data for satellite-based crop prediction models. Before I get started, I wanted to acknowledge the source of funding for this research, which is the Bill and Melinda Gates Foundation through the Enabling Crop Analytics at Scale initiative. If you're interested in this topic, I strongly encourage you to visit cropanalytics.net. The overall driver of this research is the fact that satellite-based crop type predictions are useful. We have fairly high resolution satellites, such as the 10-meter Sentinel platform, which image the Earth on a regular basis over and over again. The raw imagery, such as that shown on the right, is useful, but classified satellite imagery, showing crop types, for example, over an entire country for multiple years and seasons is more useful, as it shows us what crops are growing where and can map the changes from season to season and year to year. However, in order to develop predictive satellite models, you have to provide the model with training and evaluation data. Training data to form a correlation between spectral signature and crop type, and evaluation data to see how well the model is performing. In the image to the right, you can see three examples of label points, maize, forest, and banana, from one of our study sites in Rwanda. Models require hundreds, if not thousands, of high-quality training points. The more, the better. The problem is that training data are not typically available for the season and location where crop type mapping is being done. So it is generated on a project-by-project basis and is costly and time-consuming to produce. Field observations are gathered by teams of staff members who walk to fields and record the type of crop, as well as other data, and its location or extent. These data are generally very good, but can suffer from interpretation and geopositional errors. Here are the Sentinel-2 grid cells that contain field observations for one of our study sites. The 11-member team was able to generate 422 labels in a single day. So that's roughly 88 human hours. An alternative to field observation is to use high-resolution drone imagery, which is usually less than 4 centimeters, to identify crops and produce labels. This is done in an office environment. Our staff generated 523 labels in the same project area, taking 25 hours to do so. That's more labels in less time than field observations, but there is still a fair amount of human effort, and of course this requires drone imagery. But what if you could automatically generate labels from drone imagery using examples of crops such as banana, maize, and forest shown in the images to the right to train a computer vision model at this level? You could use the model to classify the entire drone image as compared to the 523 random locations done by humans. Every Sentinel cell is classified as one of 6 land covers shown on the right. The model runs fast and generated approximately 7,500 labels from the drone imagery in just under an hour, with virtually no human labor. The table at right clearly shows that using a computer vision model produces far more labels in far less time. It does require drone imagery, and of course the computer vision model has to be developed in the first place, but the model can be retrained with continuously added crop and land cover images across time and space. This has the potential to greatly reduce the human effort needed to develop training data for satellite-based crop prediction models. Thank you very much for your time.